हेलो अभिनव।
यस सर।
अभिनव, ये अभी लास्ट क्लास है तो अभी एक कोई व्हाट्सएप ग्रुप अपन फॉर्म कर सकते हैं क्या? मतलब इंटरेक्ट करने के लिए आपस में, कोई अगर प्रॉब्लम आता है एग्जाम तक, मतलब उसमें सर नहीं रहेंगे, बस अपन रह सकते हैं।
हाँ सॉरी।
मेरे पास सबके कॉन्टैक्ट नंबर कहाँ से आएंगे?
क्या?
कॉन्टैक्ट नंबर नहीं है मेरे पास सबके।
नहीं मतलब मैं यहाँ पे ईमेल आईडी मेरा डाल दूंगा, तो मतलब जिसको जो इंटरेस्टेड रहेगा वो कांटेक्ट नंबर मुझे मेल करेगा तो मैं वो बना दूंगा। क्योंकि ये क्लास के बाद कोई इंटरेक्शन, मतलब मतलब फॉर दिस पर्पस आल्सो कुछ रहेगा नहीं अपने पास।
ठीक है,
तो
आप
सर
कर
सर
लीजिए। हम और क्या, व्हाट्सएप ग्रुप बना लीजिए आप, है तो।
क्या?
व्हाट्सएप ग्रुप कैसे बनाना है बताइए, क्या कर रही है?
मतलब मेरा ईमेल आईडी डाल दूंगा, जो कोई इंटरेस्टेड रहेगा अपन उसमें मैसेज में लिख देंगे। जो इंटरेस्टेड रहेगा वो कांटेक्ट नंबर और नाम मेल कर देगा।
चलेगा, कोई दिक्कत नहीं है, चलेगा।
ओके ठीक है, क्लास के टाइम पे बोलते हैं जब बाकी मेंबर्स आएंगे।
हाँ, ये तो पहले भी बात हुआ था, बट हुआ नहीं, इसमें इनिशिएटिव किसी ने लिया नहीं।
अच्छा, इससे पहले हुआ था क्या?
बट इनिशिएटिव उस टाइम पे लिया नहीं था किसी ने, पहली क्लास में ही बात हुआ था।
हाँ अच्छा ठीक है, ओके ट्राई करते हैं। ठीक।
ठीक है, ओके रोहित।
Hello. Should we start the class or should we wait for a few more minutes?
तो
स्टार्ट कर
5 मिनट।
You guys have any doubts or anything you want me to discuss in particular?
नो सर, नो डाउट्स एज सच।
Wait for a few more minutes because hardly anyone is joining. So there are few things in Aspen like optimization and sensitivity analysis. Few blocks I could not cover as in the calculation block. Did you go through that part?
नहीं सर, ऐसा तो नहीं है।
So in the last video of मतलब सर ने जो पढ़ाया है उसमें क्या सर ने कवर किया लास्ट वीडियो?
बस सर वो तो देख लिया सर, वो सर ने जो लास्ट लेक्चर था वो तो देख लिया था सर।
लास्ट लेक्चर में सर ने क्या कवर किया?
सर लास्ट लेक्चर में सर ने यूटिलिटी के साथ कॉस्टिंग करवाई थी।
अच्छा।
हेलो।
हाँ हाँ, आई एम एबल टू
तो ये लास्ट लेक्चर में सर, ये सर ने डिफरेंट एक केस स्टडी लेके यूटिलिटीज के साथ कॉस्टिंग ली थी, जैसे इलेक्ट्रिसिटी से कितना कॉस्ट आएगा, और स्टीम ले लोगे और उसका डायनेमिक्स थोड़ा चेंज किए थे कि प्री हीटिंग कर लो, उस टाइप से कैसे कॉस्टिंग सेव हो रही है, तो वो कराया था। और लास्ट वाले वीडियो में सर ने डायनेमिक कराया था, लेवल कंट्रोलिंग कैसे करनी है वो सब।
डायनेमिक्स में कितने एग्जांपल्स पे?
सर एक एग्जांपल था उसमें लेवल कंट्रोलर और टेम्परेचर कंट्रोलर, दो चीज़ों को सर ने बताया था।
एक्चुअली येस्टरडे मतलब कल का जो क्लास था उसमें जो मैंने क्वेश्चन सेट किए थे वो तो कुछ डिस्कस हो नहीं पाए, तो मैं ऐसा करूँगा दैट आई एम गोइंग टू गिव यू वन प्ले लिस्ट, ओके, वेयर देयर इज डायनेमिक्स of different processes. You can go through that, and I am going to solve one problem on flash ROM where there is a flow controller, a level controller, and a pressure controller. Like 3 controllers will be there. I'm going to solve that one. And the remaining problems, they are very much like similar to the problems that we have solved up till now. Like flow sheeting problems that are there, like big flow sheet problems are there.
सर
Because
एक लेवल कंट्रोलर करेंगे सर, मतलब जो वेसल लेके उसमें सर कुछ डाटा जो लेवल वेसल का
I'll
डाया
show
और
you how to. I'll show you how
वो
to
चेंज, वो भी
extract
चेंज
this.
कर देंगे सर एक बार।
You want to change that?
यस सर, एक रेगुलर मतलब एक अपना प्लांट का डाटा डाल के जैसे पता कर सकते हैं कि वेसल कितनी देर में भरेगा, उस टाइप से पूरा एक कैलकुलेट हो जाएगा। एक तो आप जो भी बनाएंगे सर उसमें थोड़ा सा डाटा चेंज कर देना बस।
Okay. So how do you want me to start the class? Do you want me to start the class with the dynamics first and then go to the other problems, or you want to solve the other problems first and then go to the dynamics?
आप देखिए जैसे बेटर लगे सर, आपको देख लीजिए सर।
Okay, so it's better that I start with the problems that we have done up till now, because by that time I think more people will join, and then we can go to the dynamics at the end. So let us start with the class now. So the first problem is going to be an optimization problem. So the input components, we have methanol, carbon monoxide and hydrogen, dimethyl ether, water and carbon dioxide. So the process that we are going to choose is NaTl, and it is going to be done through an R equilibrium reactor. The feed temperature is given to us 260 degrees Celsius, 60 bar, 1 kilomole per hour of carbon monoxide and 1 kilomole per hour of H2. And the reactor conditions are given. The temperature is 260 degrees Celsius, that is, it is operated at the feed temperature. The pressure is at 50 bar. We have to optimize the reactor temperature to maximize the conversion. Okay. So the reaction is given to us. So 2 carbon monoxide. So 3 reactions are taking place. 2 carbon monoxide plus 4H2 gives 2 CH3OH. Then 2 CH3OH gives dimethyl ether plus H2O, and carbon monoxide plus H2O gives CO2 plus H2. So try to solve this problem first. So we are going to use an R equilibrium reactor for this problem. Before performing the optimization, you need to do a sensitivity analysis as to see how the reactor temperature is affecting the conversion. For conversion, what we usually do is we like find out the conversion of the products, that is the fractional conversion. You don't have to find out the fractional conversion. Try to find out the amount of product that is coming out in stream 3. Okay, and what is the effect of the temperature? If we like whether decreasing the temperature, increasing the temperature increases the product flow rate in kilomole per hour in stream 3, find out that.
So should we wait then for
If there is any doubt in any step, ask me.
Sir, approach temperature would be 260, right?
Yes, yes.
So for all the reaction, approach temperature will be 260, sir. For all the three reactions.
Sorry, what reaction?
सर तीनों रिएक्शंस के लिए अप्रोच टेम्परेचर 260 रहेगा ना?
Yes, it is given that the reactor condition and the feed temperature are 260 only. But you have to optimize this part. This temperature, it is just an assumption.
ओके सर.
So how are you guys solving it? Can you share your screen and show? Rohit or Abhinav, anyone can share your screen and show.
2 seconds.
So did you? This is you are defining the reaction, right? Okay. Yes, yes, you're going right. Yes, fine. Third reaction will also be good. Have you taken the screenshot of the problem that I've shared?
Yes sir, I've taken the screenshot.
Then it's not a problem. Yes, go ahead.
Because I'm typing from here, otherwise it's very difficult if you change the screen, sir.
Yes, yes, yes.
Sir, I have got results.
Okay. Okay, then you share your screen and show us how you're done.
Okay, sir.
So this is for, did you optimize it yet or you have just simulated?
Just simulated.
Okay, okay. Show the simulation, the field specification, and then the reactor specification. This is the reactor specification. 260 50 bar. Okay. This is the reactions. Okay. Fine. Now start with the sensitivity analysis. So what is the uh, important compound in this reaction?
CO2 and hydrogen.
I think it is DMC, no?
The dimethyl ether.
Yes. We have 50% of CO2 and then 50% of hydrogen. I think this is methane steam reforming. What reaction is this? You have to find out what is the important product that you are getting. We are getting methanol. Methanol is getting converted to DME and water. Then water is reacting with carbon monoxide with CO2 and hydrogen. I think hydrogen is the product that we have to focus on.
I think it's methanol.
Methanol, but we are not getting methanol in product. Only look at the stream results. Stream results. We have hydrogen and carbon monoxide. So hydrogen is our product.
Hydrogen.
Yes.
Sir, but hydrogen is our feed, right? CO and
Hydrogen.
hydrogen is our feed.
Yeah, that is yes, yes. Okay, then see how you can improve the conversion. CO. So from CO we are getting methanol. So do the sensitivity analysis.
So what would
Yes.
we vary?
What you are going to vary, you are going to study the temperature of the reactor and how is it affecting the mole flow of methanol.
Okay.
So the manipulated variable is the temperature of the reactor. So the type of the variable will be,
Methanol or DME, dimethyl ether.
let us study both. We are going to see how it is affected. Log variable. Now you have to select the variable. आप ठीक कर रहे हो, फिर वेरिएबल पे जाइए, वहाँ से फिर टेम्परेचर ऑफ द रिएक्टर सिलेक्ट करना है आपको.
Where is the temperature of the reactor?
In the variable drop down, go to that. See, in block you have defined B1. Now just below it there is variable. There is this arrow. Select that arrow.
So I'm already in it.
No, in my screen it is showing that you have not still selected that. Select that arrow over there. Yes, click it. Are you sharing your entire screen or just the window?
A window.
Try to share the entire screen, then I'll be able to see everything that you are accessing. Now it is visible.
Okay, sir.
Now go to variable. Yes, from here you have to select temperature.
So only one temperature we have.
Yes, that is already temperature.
Okay.
Select. We have defined it in degree Celsius, right?
Yes.
So now over here, the starting point we had taken 260.
Hmm.
So take it from 200 to 300 and increment, give 5 degrees Celsius. Okay. Now I have to define the variables.
Uh, Mole flow of.
So you have to maximize the mole flow of methanol and DME. So
Okay.
you have to study the how the mole flow is varying in methan with the change in temperature.
Mole fraction. Right.
No, select mole flow, not mole fraction. If you select mole fraction, then it will like you have to define the fractional conversion equation there. But if you select mole flow, then it will come to you as a product.
Okay.
सर क्या फर्क पड़ेगा सर अगर मोल फ्लैक्शन कर देगा तो सर
So it will like you will get a fraction. No, I think it will be better if we select mole flow instead of mole fraction. Although both are related, if we increase the mole fraction, then the mole flow is going to get increased only because it is a mixed stream. You see the results. You can plot the results if you want. It will be better if you visualize how it is varying.
Uh,
Yes, go to plot, select the arrow. No, don't have to write custom. There is results curve. Yes, select that. So this is how it is varying. So methanol kilomole per hour and DME kilomole per hour. As we increase the temperature, the
Decrease the temperature.
sorry. So we have to
As we
decrease the temperature. Yes.
temperature. Yes.
So the mole fraction is higher if it is below 260 degrees Celsius, right?
Yes, sir.
you can say that means it's an exothermic reaction.
Yes, you can say that also. So now optimize this.
variable would be temperature, right? Again.
Yes. No, here you have to the
Log
In
query
D,
for
okay.
this is going to
Uh,
be your difference. So select one product that you want to increase. Let's say DME.
से यहाँ जो मैक्सिमाइज हम लिखते हैं इसमें नंबर भी लिख सकते हैं क्या? DME greater than 95 or something like
In
that.
that case, you have to add constraints.
अच्छा, एक बारी कर ही लेते हैं, कांस्टेंट पे ऐड कर दीजिए.
Okay. So do one thing. Go to the
Yes, sir.
sensitivity results. So over here, we can see that DME it is increasing, right? To select one particular value, let's say the temperature of 210, what is the DME value? 0.00716, right?
yes, sir.
Put a constraint such that the concentration of a DME of your DME is more than this value.
Okay.
क्योंकि सर सेंसिटिविटी बहुत बारी कर लिया, अच्छी तरह आ गया. ऑप्टिमाइजेशन में थोड़ा थोड़ा इशू आ जाता है कभी कभी बीच में, इसलिए.
So select new over here. Selected. So this is DME, right? So you have to select new. Okay. Now we have to define the constraint. Okay. So no, you cannot define it from here. See in your left there is one constraint folder. Yes.
Yes, sir.
Now select open this folder in your left. Yes, yes, it's fine. So now over here you have to again define that variable.
Should be okay.
Okay. Now define that variable like you have defined. Now come to specify. Now write the name of the
DME फ्लो लिखा ना, वही वेरिएबल का सेम नेम कॉपी करना है.
in the but you have to write it just the way you have written. Yes, it should be in capital. Now greater than equal to, write that value of yes, fine. And tolerance give point 0.000. Yes. Now come to objective function input. Optimization is done. Objective and point, now we have to vary. So we are varying the temperature. Give the same lower limit 200 to 300. 5. Now run this. The following blocks were completed with warnings. You have got the result. So that is the maximum we have got, right?
Yes, sir.
Now go to manipulated variable.
So both values, initial and final, are same. Can of not an
It
issue.
is, no, you will see it in the, go to manipulated variable. So previous value was 260, right? Now this is the value
Sir,
that we have got, 200.
can we vary it from 100 degrees Celsius?
Yes, try to vary, see what happens. You're going to get a different answer. It is the sensitivity analysis that picking up the volume. Go to results of optimization. But no results are showing.
Result is not showing, sir.
Deactivate the sensitivity part. Uh,
Delete.
no,
Should I delete it?
go to the S1 folder.
Okay.
Right click,
Hmm.
right click, right click on the
There.
folder.
Okay.
Deactivate. Now reset the entire simulation. Okay. Now run
And
it.
deactivate means that will not take part in the
No,
that
no,
in the
that block.
simulation.
No, no, that block will be omitted.
Okay, normally we used to delete.
Should I run now?
Yes, yes. What is happening? Sorry, some problem is happening.
Yes.
Try to reduce that temperature, lower bound temperature that you have taken. Take it from 100 to 200 and see if it is happening. So with the Aspen software stop now.
Sir, why did it stop?
Uh, it
Okay.
happens sometimes, it crashes. But you have understood how to do it, right?
Yes, sir. Yes, sir.
So let us do the next problem. So these are the types of problems that you are getting in your assignments. So over here, the questions, they are a bit long with a lot of data. So try to take screenshot of this problem. Okay. It is not that difficult. It is a very straightforward questions are there. It's just that the process flow sheets, they are a bit complicated. So a hydrocarbon stream H is supplied at 5 degrees Celsius and 2.5 atmosphere. The pump P1 discharges the feed at 10 atmosphere. In table 4.1, the component-wise flow rates are tabulated for stream H. The schematic representation of the complete process integrated with a pump and 5 DSTW columns, that is C1, C2, C3, C4 and C5, are shown. For Aspen plus simulation of the distillation train, the required information are given. So the name of the columns are given, C1, C2, C3, C4 and C5. The condenser pressure is given and the reboiler pressure is also given. All distillation models have 20 theoretical stages, including condenser and reboiler, and a total condenser. For the light key and heavy key, we expect 99.9 and 0.1% recovery respectively in the distillate of all columns. Using the Penn-Robinson property method, simulate the distillation train and report the composition of all distillation products. So let us solve this problem. So I will also solve, you also try to solve it parallel. Okay. So take a screenshot of this problem. So there are a total of 5 DSTW columns. And this is the specification in which we have to operate.
So जैसे पहला कंपोनेंट C1 दे रखा है.
Yes. No, it is the
C1
abbreviation. It is not the component C1.
सर तो C1 C2 मतलब ये तो वही हो रहा है ना सर, मीथेन इथेन प्रोपेन
Yes,
NC5 इसी टाइप से दिया है.
technically that is what will happen, because depending upon the weights. Yes, tell me what is the.
सर C1 के लिए फिर पंप लगा रखा है तो पॉसिबल नहीं है ना, गैस में पंप दे दिया है.
Acha, with that respect you are telling. That is true. But the 2.5 atm, 5 degree Celsius. Yes, this is right. You cannot have a pump if the feed is gaseous. Then do one thing. Keep the temperature same, feed temperature. Just increase this 2.5 to 10 atmosphere and then omit this pump. Now assume that the feed is coming at a 10 atmospheric pressure, because the pump is only required to increase the pressure. No, remove this pump.
ठीक है जी, ठीक है. और सर ये IC4 भी 2 बार ही दे दिया, वो एक NC4 होगा, IC4.
हाँ, ये भी चेंज कर लीजिए आप. C1, C2, C3, IC4, IC2, IC5, IC4, IC6. Then Robinson property network. The interaction parameters about data. So property analysis. So we have 5 DSTW columns. 1, 2, 3, 4, and 5. So this is C1, C2, C3, C4, C5. So we have the field. So as discussed, I'm removing the pump from here. So we have the products. This is your field. This is D1. Specification 5 degrees Celsius, 10 atmospheric pressure. Next is our mode flow. So C1 is 10, C2 is 35, C3 is 50, IC4 is 130, NC4 is 200, IC5 is 180, C5 is 10 to 1. I forgot to add another property. The component is C6. C6 is 5. Now for C1, what will be the light key component?
C1
And all the theoretical stages are
20
20. Condenser pressure
9
is
9 9
9
9
and 9. 9.
atmosphere.
So this is C1
C1
and
point
above
nine
this
nine
is 0.99.
point 999.
Okay. Heavy key?
C2 C2 दिया सर
Okay.
0.001.
Number of stages here also 20. What is the, this is 5 and 5. 5 and 5. Atmosphere. Atmosphere. Here, what will be the component? C2.
Yes, sir, C2 and light key is C3. Heavy key is C3.
This is our C3. 20. So our light component is C3. Heavy component is, what should be a heavy component? IC4 or NC4?
IC4 will be sir C3. IC4 will be the heavy component. Sir.
This is 4. For C4, it should be IC4. This should be NC4. Am I right?
सर जो उसमें लास्ट कंपोनेंट हेवी में डाला है वो इसका लाइट हो जाएगा, बस इतना ही कर रहे हैं.
So what component will be here? NC4. And the light heavy key component will be IC5. So we should add some 2 more columns. Okay. So we look at all the results from here. C1 is maximum over here. And C4 is maximum. But I think the maximum should be NC6. Fine. This was a very easy problem.
इससे इसमें ये हम पता कर सकते हैं कि इंडिविजुअल रिबॉयलर में स्टीम कितनी है?
You can find out the heat. I think, but let me check once.
हीट तो सर हीट ड्यूटी तो बता देता है, जैसे हम एमपी स्टीम दे, एचपी स्टीम दे, उसमें कितना स्टीम फ्लो लगेगा, वो सब पता कर
You
सकते हैं.
have to add this then. Let me see this option. Block options. No, it is not available over here, but I think in red flag column it is there. You can add utility stream for calculation. I think so. There is another way you can do it. If you turn this on now, it will give you the cost of the unit operation that you are handling. So over here you can see it is showing that it is driven by electricity, but you can change this also. Usually it is given over here if you want to add any utility stream or not, but since it is a shortcut distillation method, that option is not being shown.
तो कोई पुराना सेव प्रॉब्लम खोल के बता सकते हैं?
Save problem. I can show you one problem that I work on. It is my research problem. I can show you that. Is my screen visible?
यस सर.
So this is actually a downstream process that I have designed for my current problem over here. So what I have done is, for example, this is a condenser over here. So I need to find out the utility that is required. No. So over here I have defined the utility. So utility, I have defined the electricity and I have defined the water as the cooling utility that will be required. So for this condenser over here, if I select this, so once I've specified over here, there is a utility option. So I have to select this utility ID as water. So naturally that calculation will happen as to how much water is being required. So if I come over here, that calculation will be done over here. In this economic analyzer, it is going to estimate the total amount of water which will be required in my process. And to define the utility, it is defined usually over here. So you can give the purchase price of water, or
ये तो देखा है लास्ट वीडियो में यही था, 12th वाले वीडियो में ये सभी बताया था.
and then inlet outlet conditions you can fix, as in how much temperature difference you want. So this is how you can calculate the utility.
ओके.
Let us go to the next problem. This one is a very big problem, so I'm going to give you 15 minutes time to solve it. And I'm not going to solve this problem. This is very easy. This is not much difficult. There is this compressor, flash, and a stripper. Do you want me to solve the short problems or do you want me to solve the long one? Which one do you want me to solve?
Yeah, you solve the difficult problem. If it is long or short, it's easy. We can do it ourselves.
Okay, then I'm going to solve this problem. This problem also I can solve. Okay. So two problems will be there which you can practice on your own. Okay. So over here we have the process flow diagram of vinyl chloride monomer manufacturing plant, and this is the flow sheet of the plant. The flow sheet has been developed based on the VCM production technology which is being reported in CDAP. So we have a mixer which is coming inside a reactor, then there is another mixer, it is going into a heater, then to a pump, then again to a heater, then again a reactor, then two heat exchangers, then two distillation columns, and finally to a splitter from where a stream is going to purge and the remaining stream is going back and is mixing with the outlet of this reactor over here. So take a screenshot of this process flow diagram first. So this is the question from which, this is the question statement. Take a screenshot of this as well. So pure ethylene stored as a gas at 70 degree Fahrenheit and 1000 psia with a flow rate of 20 tons per hour, and pure chlorine stored as a liquid at 70 degree Fahrenheit and 150 psia with a flow rate of 50 tons per hour enter the mixer block B1 operated at 2 atmosphere. The mixer outlet F1 then goes to the reactor B2 run at 363 Kelvin and 1.5 atmosphere. In this stoichiometric reactor, the following chlorination reaction occurs with 98% conversion of ethylene to 1,2-dichloroethane. So this is the stoichiometric reaction that is taking place. In the next, mixer B3 operated at 1.4 atmosphere allows the mixing of the recycle stream F12 with the reactor product F2. The outlet stream F3 is then condensed fully to liquid phase in block B4 at 298 Kelvin before being pumped to an evaporator. The pump B5 has discharged the liquid at 26 atmosphere. The evaporator B6 performs the phase change operation, and then the vapor temperature is increased in the same unit to 515 Kelvin. In the subsequent step, stream F6 is introduced in the reactor B7, which is also a stoichiometric reactor, in which the following pyrolysis reaction is taking place. So dichloroethane is changing to VCM and hydrogen chloride. The dichloroethane converted to VCM and it takes place spontaneously at 773 Kelvin and 25 atmosphere with 65% conversion. To reduce the carbon deposition in the heat exchanger, the hot vapor stream leaving the reactor is quenched in block B8, yielding a saturated vapor stream at 443 Kelvin. Quenched effluent stream F8 is condensed to liquid phase in block B9 at 279 Kelvin and then fed to a DSTW column B10 as stream F9. In the next stream F10 is introduced in another DSTW column B11. The first column mainly separates HCl from other components, while the second column purifies VCM from the rest. Both distillation columns have 10 theoretical stages, including condenser and reboiler, and a total condenser along with the specifications. Finally, block B12 F-split splits the stream F11 to ensure the recycling of 99.999% of F11 and F as F12 stream to mixer B3. A purge stream is introduced to prevent accumulation of unreacted components. Using the poly-SRK property method, simulate the complete plant to compute the composition of all streams. So there are three parts of this question. So this is the first part. Take a screenshot of this part, take a screenshot of this part, and then this one. Read every line. All the data that is required for simulating this problem is given, and there are no errors in this problem. You can easily simulate the problem if you read the question properly. All the input and output conditions are specified over here. So just try to simulate this problem. Take, so now I think it is 7:05. So take 15 minutes, try to solve this entire problem. Is there any doubt?
No, sir.
Sir, excuse me. Hello, sir.
Hello? Is it done? So first we have to specify the components. The components are ethylene, chlorine, dichloroethyl. Then we have the vinyl chloride monomer and hydrogen chloride. So this ethylene. If there is any doubt, you can ask me.
Hello, sir.
Yes.
Sir, if time permits, after that, can you solve assignment 2 part B question?
Assignment 2.
Assignment 2 part B. In that, I have used Penn Robinson method, but I am not getting the right answer. A different method also I have used. The answers are not matching with the given answer.
I think we have discussed this problem, right? You had asked me the same thing about Payne Robinson method. I told
No,
you
this is
to.
a
Did they
no.
specify
This is a
the Did they specify the method name specifically?
no method is not given actually. This is a assignment 2.
Okay. So if the method name is not given, then through method assistant, whatever you have chosen, then it should be correct. You can like mail the NPTEL regarding this. That is the group mail that you have. You can mail that. Someone else had asked the same problem. It was the same assignment, sir. I think week 2 assignment only. You two had the same problem.
Same assignment week 2.
Yes, yes. Over there also there was some problem regarding the method name was not specified, so he has done it with method assisted, and then the answer did not match. It will be close, but it won't be within the range that is given in the answer. Is this the same problem that you have faced?
Yes, sir. Answers are
But it is close,
not
right?
match. Not that much closer. Answers are different. If time permits, can you just check after this?
Okay. So has anyone been able to solve this problem entirely or partially?
Just now the block diagram has been made.
Okay, take time. What are these columns? These are DSTW columns.
Yes, sir.
CO4 and CO3. This is CH4. This is CO2. This is the plasma is big. This is the two. This is a 3. Then 3, 4, 5, 6. 7. So this is our entire block process machine. So now we have to specify the input streams. The dichloroethane is converted to this index matrix of which we can get 65% conversion. Urethylene stored at 70 degree Fahrenheit and 1000 psi pressure. So 70 degrees Fahrenheit and we have 1000 psi pressure. With a flow rate of 20 tons per hour. So this is a mass. So we have 20. This is tons per hour. 20 tons per hour. Tons per hour. Next we have chlorine. What is the condition of chlorine? 70 degree Fahrenheit, 150 psi pressure. So 70 Fahrenheit, 150 psi pressure. 50 psi pressure, and the mass flow is 50 tons per hour. So mass flow, this is 50. Enter a mixture block B1 operated at 2 atmosphere. So next, so this is our mixer. So the pressure is operated at 2 atmosphere. We save this LCD. Close this thing to some point. VCM production. Now this is our B2, that is our then moves to reactor B2, which is run at 363 Kelvin and 1.5 atmosphere pressure. 363 Kelvin, 1.5 atmosphere pressure. In this stoichiometric reaction, the following chlorination reaction occurs with 98% conversion of ethylene. So 98 conversion of ethylene. So this is gas, this is liquid. So the valid phases is going to be vapor liquid. Next we have to define the reaction. So mu enter the stoichiometric reaction mu ETH and we have chlorine and the product is dichloroethane. Dichloroethane and the fractional conversion is 98%. Of ethylene. So B3 is complete. Now coming to B4. So what is our B4? So it is B3. B3 is a mixer. So B3 is operated at 1.4 atmosphere pressure. This is defined. Now we are coming to B4. What is B4? That follows the mixing of the recycled stream F2 with the reactor product F2 and the outlet stream F3 is then condensed fully to liquid phase in B4 at 298 Kelvin before being pumped to an evaporator. So it is fully condensed to liquid and the temperature of is 298 Kelvin. So this is 298 Kelvin and since it is fully condensed we have to give the vapor fraction and we have to give the vapor fraction as 0. So B4 is complete. Now coming to B5. The pump B5 has discharged the liquid at 26 atmosphere pressure. So discharge pressure 26 atmosphere. The evaporator now coming to B6. B6 is our evaporator. The evaporator B6 performs a phase change operation and then the vapor temperature is increased in the same unit to 515 Kelvin. So phase change is happening and then the temperature is increased to 515 Kelvin. So here we are going to specify the vapor fraction. The temperature is 515 Kelvin and here the vapor fraction is going to be 1. That is, entire feed is converted into vapor since phase change has happened. Now we are going to B7. Let us come to B8. Let us go to B7 first. So B7 is another reactor. So in the reactor B7 in which the following pyrolysis reaction takes place. So this is only vapor only since only vapor stream is coming now. And dichloroethane gets converted to VCM and hydrogen chloride. and it takes place spontaneously at 773 Kelvin at 25 atm pressure. So 773 Kelvin and 25 atmosphere pressure. Coming to reactions. So what is happening? So this is the reaction. Dichloroethane gets converted to VCM and hydrogen chloride. So dichloroethane gets converted.
Sir, what we need to compute finally?
Compute the composition of all streams they are asking. So
Okay,
try
sir.
to find out the composition of the product streams. Have you completed it?
Yes, sir.
Okay. Next, it is 65% conversion. So 0.65. And the conversion is with respect to, okay, there is only one reactant. So this is done. We are coming to B8. To reduce, the reactor is quenched in block B8 yielding a saturated vapor stream at 443 Kelvin. So it is a saturated vapor stream. So vapor fraction is going to be 1 and this is 443 Kelvin. Okay. If it is condense to liquid phase in stream F10 and is introduced in another DST tube up to B1. So, if it is 279 Kelvin. So 279 Kelvin. So next is our B9. This should also be a heater. Yes. So temperature is 279 Kelvin. And the vapor fraction is 0. And it's then got a BSTW column B10 as stream F9. In the next stream F10 is introduced in B11. The first column mainly separates HCl from other components, while the second column purifies VCM from the rest. Both the distillation columns have 10 theoretical stages and the total condenser along with specification as shown in figure table 4.3. So first we are going to come to B10. Okay, so B10 number of stages are 10 theoretical stages. The condenser pressure is 20 atmosphere. The boiler pressure is 22 atmosphere. The light key component is given HCl and the heavy key component is given VCl. So how much? 99.9. So 0.999 and this is 0.001 and total condenser is given. Next we are going to come to B11. So in B11 number of stages are 10 and the component is light key component is VCM over here and it is 999 and the heavy key component is dichloroethane. This recovery is 0.001. The condenser pressure is 7.5 and 8. So this is 7.5 atmosphere and this is 8 atmosphere. Okay. Last is our B12. This is a splitter. B12 splits the stream F11 to ensure the recycling of 99.99% of F11 as F12 stream to mixer B3. So F12. point. So all the required inputs are complete now. So CO2 has zero flow in the output stream.
फिर एफ स्प्लिट बताना क्या डरा था एफ स्प्लिट में
99.999%. So that will be the split fraction will be in point. Converted into fraction. What is the problem? Rohit, have you been able to simulate the problem?
Pardon, sir?
Have you solved the problem?
Yes, sir.
So did you get the answer?
Yes, sir.
Okay. So over here in my simulation it is showing me one error. I'm not being able to understand where the error is. It is not telling me the control panel flowing is zero flow rate in the output stream. Right? These are all the Okay, show me your answer once. Some mistake in the simulation.
Yes, sir. I share my screen.
Okay. show me the VCM mole fraction in this.
हाँ T1 it is 0.9786
Okay.
and in T2 VCM is 0.9896.
Yes, it's correct. This is correct. Okay, so you can see this problem and you can try to solve it on your own. There is some error that I have made probably in inputting the values over here. So try to redo this on your free time. There is nothing that is like complicated in this problem. All the data are available in the problem. You just need to put the values properly and then it will be done. What I want to show you is I want to demonstrate one dynamic problem before we end the class. So let me go to that first. So there are multiple problems of this type that I have given over here. I thought of solving this problem as well, but we don't have that much of time. So we are going to perform this simulation that we are going to simulate the dynamics of a flash drum.
So please share your screen.
So this is the problem that we are going to solve. This is the dynamics of the flash drum. So we are going to perform a simulation of a flash drum. The feed contains 60% of C1, 10% C2, 10% of C3 and 20% of IC4. The feed is flowing with 100 kmol per hour at 30 degrees Celsius and 30 bar pressure. We are going to use Penn-Robinson thermodynamic property method. First we have to perform the steady state simulation and then do the dynamic simulation. So we have to take the pressure drop across the control valve to be 5 bar. Okay, so it is given in the figure over here. So let us specify the components first. We have C1, then C2 and C3 and C4. C2, and then we have C3, and we have IC4. And we are going to use Penn-Robinson method. So we have 3 control valves and a flash drum. So over here we are going to take the separators flash 2, then pressure changers. So we have one valve over here, one valve over here, one valve over here. This is the side of the valves. So this is the fluid that is flowing. Now we have to specify the feed. So for doing a dynamic simulation, it is very much similar. Like for updated steady state simulation, everything remains the same. So we have 30 degrees Celsius and 30 bar pressure. So 30 degrees Celsius and 30 bar pressure, and the mole flow is 100 kilomole per hour. 100 kilomole per hour. Next we have mole fraction. So C1 is 60%. C2 is 10%. C3 is also 10%, and C4 is 20%. This is equal to 1. Next, we have to specify the temperature and pressure of the flash drum. So let us perform adiabatic flashing. Pressure drop, let it be 0 bar. Yes, over here it is said that delta P is 0 bar. There is pressure, and then doing adiabatic flashing, that is, there is no heat exchange that is taking place. 5 bar, this is 4.
Sir, you wrote 0 bar pressure for the flash drum.
No, it is okay. That this delta P means equals to 0, that pressure, if I specify, that is also pressure drop calculation.
Okay.
So this is 5 bar. This is C2. This is C3. So C2 is our vapor, so here this will be vapor only. Pressure drop is 5 bar. This is our liquid only. This is also.
Does it create any changes if you don't change liquid or vapor?
No, but it is for, but it is good practice. Okay. So we have got our results. Okay. Now if we turn on this economic analyzer, so if we have turned on this economic analyzer, from here we can get the dimension of the flash drum. If we come to here, so over here you can see that the liquid volume, the vessel diameter, and the vessel height we are going to get from here, from this economic analyzer. Okay. Now what we are going to do is we are going to come to our flash drum. That is this P1. Okay. We are going to come to dynamics, and we are going to select the dynamic mode. Once we select the dynamic mode, we are going to come here in dynamic. Okay. So here it is setting instantaneous. We are going to consider a vertical cylinder. So in vertical cylinder, the length and diameter of the vessel can be given through here.
So we can change it also.
Yes, you can give your own values also, but I am going to give the value that I found out from. Okay. So here you come to the dynamic part. Paste. So this was a diameter, right? is the well. Diameter is 0.9 and the length is 3.6576. So now we select next. And we click on OK. Now that is being done. Now we are going to select this pressure checker. It is said that the flow sheet is configured to be fully pressure driven. Now what we are going to do, we are going to select this pressure driven. Now it is going to ask for a directory where you want to save it, and it will be saved as a different file, Aspen plus dynamic files. So you click on save. So once you click on save, your Aspen plus dynamics file will open. It's taking some time.
प्रेशर ड्रिवन का क्या मतलब हुआ?
It means that your entire simulation is correct and you can now like develop the dynamics of the simulation. It is just a checker whether to see that your entire simulation is correct or not. So here we have one pressure, we have one level controller, and here is one pressure controller. We are going to add one more controller. So over here, instead of previously we had only material stream, now we are going to do control signals. So what we are going to control, we are going to control the mole flow of the feed. So this is coming over here. This is our process variable, and this is our operating variable, which is going to come to this C1. Okay. Now we have to specify the action. We have to specify it as reverse because, sorry, but before that, make sure that you change it to initialization, this status over here. Now you come over here, you come to this configure and you are going to do reverse and you select this initialize variable. So naturally we had given 100 kilomole per hour as our simulation, steady state simulation. So that value gets updated over here. Okay. Now what we are going to do is we are going to study the simulation at this point. So remember, this PC is our pressure controller. Okay, this is the level controller, and these values that you are seeing over here, they are all being tabulated from the steady state simulation. Now before doing it, we are going to go to run, options. We are going to convert this mode to dynamic, and instead of, we are going to reduce the time so that we can see the changes properly. Okay. Now what we will do is we are going to, this is in dynamic mode. This is the plot, results plot for the flow controller, that is B2, this one. Okay, and we will see the variation of, let's say, the level over here. Now this is in dynamic mode, and now I'm starting the simulation. So this has started. Okay, so initially we have not given any change to the flows over here. So it is a steady state. A straight line is coming for the process variable, that is this line over here. It is a straight line. You can see 100 over here, and a straight line is coming. We are going to wait till this controller output. You can see the process variable of the length, it is straight, it is not changing. But since we have started this process just now, the controller output we need to wait. That is the controller output of this controller C3. We need to wait till it reaches the steady state. Now you can see that it has reached a steady state over here. Okay. So now over here this was 100. Now what we are going to do is we are going to give a 10%. We are going to increase it by 10%. Now I have increased it. You can see that these changes are reflected in both the streams. I mean, now here you can see that this process variable, the height, it has first increased. So this the controller output has also increased. Now as the controller output is coming to a steady state, the height you can see it is again being controlled back to its initial state. But one thing you have to notice over here, as we have given 110, you see this value, the process variable needs to reach the set point, right? But it is taking a bit too much time. So the response, it is a bit slow. So for that, what we can do is we have to tune this controller. So let us wait till it reaches a steady state, both the level of this flash drum and this flow rate over here.
Sir, can we give the line size also, upstream of control and downstream of control?
Sorry?
Normally the upstream and downstream control line size are different. For example, upstream is 10 inch and downstream is 8 inch. Can I give like that also?
I don't think that you can, but you can try once. In the valve you are saying, right?
Yes, sir. Upstream and downstream configuration is maximum is change.
You can check it. I'm not sure about that. I haven't come across whether we can give this specification or not. So now you can see that the level controller has been brought back to its initial steady state. Now what we are going to do is we are going to tune this. We are going to tune the level, this controller over here. For tuning, what we are going to do is we are going to select this tune option over here, and we are going to select this closed loop ATV, and we are going to start the test. Once we start the test, you can see that this tuning is taking place over here. So now when the tuning is taking place, we are going to
PID
wait for a
tuning.
few moments. Huh?
This is already this is PID tuning.
PID,
PID.
yes. We have
It will
selected,
generate the PID variables.
yes. Once we will do this finish test over here. So you can get the ultimate gain and the ultimate time period you are getting over here. Now we are going to come to the tuning parameters. We are going to select calculate. So you see the gain and the integral time and the derivative time all have been calculated. Now what we are going to do is we are going to just update the controller. So once we have updated the controller, the response automatically will be fast now. Now I'm closing it. So previously when I had given it a 10% step change, you could see that it took a lot of time for the process variable to reach. Okay. Now what I'm going to do, I'm going to change this, reduce this by 10%. And we are going to see that the response of this process variable is much faster. Now you can see that after tuning, this has become much faster. So this was an example of flash drum using a level controller and a pressure controller. If you want to see the plot for pressure, that is the pressure controller, this is the valve, this is the graph for it.